So let's look at our data and calculate some z-scores. Let's say we have our owl, our subject 1 in the data. And that subject scored a 28 on happiness and a 2 on loneliness. Very happy and very not lonely. It's a happy owl, right? We know the means for 15 and 14 and a standard deviation for 10.8 and 8.5. Now we can calculate how much away is this owl from the mean in terms of happiness and loneliness. And we see 28, the mean, minus the standard deviation, 15, minus the mean, 15, divided by the standard deviation, equals 1.2. So this owl is 1.2 standard deviations above the mean on happiness, and on loneliness it's minus 1.42 below the mean. Right, so this is a very happy owl and very not lonely owl compared to our sample. And we can do this for every possible animal as well, right? So at home, try to see what happens if you do this one, get a z-score for that one. Now, so far I talked about descriptive statistics of one individual variable, like of happiness or of loneliness, but we can also see how these things relate to each other. We do that by looking at the covariance and the correlation. So the covariance is pretty much the way that we calculate the variance. Now, actually, I did not discuss that, but the variance is s squared, and that's just the square of the standard deviation, or it's basically calculating the standard deviation but not taking the square root in the end, like this, without the square root. When you once get the square root, you get a standard deviation. For the covariance, we do pretty much the same, except instead of doing the square multiplying with itself, we multiply with something from another variable. And then we can see that the covariance of a variable with itself is actually the same as the variance, because then this would be the same thing. So what are we doing here? We have 1 over n minus 1, like we had in the standard deviation and variance. We have our sum sign. And then we multiply with the distance from the mean in one variable. We multiply that with the distance from the mean in the other variable, or deviance from the mean in one variable with the deviance from the mean in another variable. So this means that this number will be positive if this is above the mean, xi, and if yi is also above the mean, or if they're both below the mean, and will be negative otherwise. The correlation is a way to standardize the covariance in a scale that's interpretable. Like the covariance is a bit hard to interpret, it's like some number, it's on squared units basically. It's really hard to interpret. But the correlation coefficient we can interpret. The way that we calculate this is by taking the covariance and dividing it by the product of the variances. And that's really it. The correlation is actually also equal to the covariance between z transform variables. That's interesting. So if you first do the z transformation and then do the covariance, you get the correlation. That's quite magical. A correlation can only be between -1 and 1. This covariance cannot exceed this number here. 1 means that the correlation is perfect, minus means that the correlation is also perfect, but just on the opposite direction. Let's see what it looks like. Here I plotted some random data on the different correlations. So we see that for 1 and for -1, right? We see that there's an exact 1-to-1 relationship between one variable and the other variable, linear relationship. So it is in a sense the same variable, but they're exactly the same. They might be on a different scale, or maybe if it is -1, one variable is like the opposite of the other one, a reordered variable, but it's exactly the same variable. If you know one, you know the other one perfectly. Right, so that's not that interesting actually. You would not expect ever to get a correlation of 1. 0 means that the points are really all over the place. Right? So there's no pattern here. And a negative strong correlation would look like this. Negative positive correlation would look like that. The further away from 0 you are, the more it becomes like a line. Like that. Okay, so let's see if we can calculate this correlation coefficient. So now we know the means, we know the standard deviations. So let's compute the correlation coefficient. Whoa, that's a lot of numbers. It takes a while, right? So maybe, write them down nicely. Now just write them all in like one line, but you can also write them below each other. I can say like, okay, 28 minus 15 times 2 minus 14, and then 0 minus 15 times 24 minus 14, etc, 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 and then write plus. It might be nice notation, but it wouldn't fit on the slide. Or take it in steps. First calculate the deviances, then square them, then sum them, etc, etc, etc. So what do we do here? We have this formula here, right? So first we compute this sum of deviances, basically multiply deviances. And we get a negative number, that's fine, right? It could be negative. And then we divide by n minus 1 to get the covariance. And then we divide again by the standard deviations, their product, to get the correlation. In this case, very strong negative correlation of minus 7.6. Right, so let's look at that. Here we have our scatter plot. So this is the same data, right? The data that we had before. Now represented on a scatter plot. So I have one variable here, one variable here. It doesn't really matter which variable you put where. I mean, normally you'd probably put the independent variable or the predictor on the x-axis and the outcome variable on the y-axis, but yeah, it doesn't actually matter, right? Anything that works is fine. Let's draw the mean. So the mean level loneliness was 14. The mean level happiness was 15. So it means these lines that represent the means, the averages. Right, so the average loneliness score, average happiness score. Then the deviances are the distances from this mean, right? So we had this example of the owl, right? That was the one that we had. And the deviance was, I think he scored 28, right? That was 28. Then the distance here, the deviance is 28 minus 15, which is 13, I think. 13, yeah. 13. Yeah, I can do mathematics. Yeah. All right. Then this hamster, for example, has a deviance of, what is it, like minus 4, minus, no, like probably like minus 9 or so, for example. Right? Those are the deviances. And for loneliness, we can also look at these distances from the mean, right? So how far away are these from the mean? In this case here, we had this very sad parrot. He was very unhappy. But also very lonely, so there's like a very big deviance here from the mean. Then the covariance is really just these deviances multiplied with each other. Right. You see here we multiply these with that, and then we multiply them, we sum them, then we divide them by n minus 1, and the correlation we get by also dividing by the product of the standard deviations. Now what you see here is that we have these 4 quadrants. Right, we have, let's say, this quadrant here, this quadrant here, this quadrant here, and this quadrant here. Right, so in this quadrant, loneliness is above its mean, and happiness is above its mean. And in this quadrant, happiness is below the mean, but loneliness is above the mean. In this quadrant, they're both below the mean. And in this quadrant, they're both, no, happiness is above the mean and loneliness is below the mean. Correct? Yeah. So happiness is above the mean here, below the mean here, loneliness is below the mean here, above the mean here. Well, that means if you multiply these deviances, here they're both positive, so we get a positive number. And here they're both negative. If you multiply a negative number with another negative number, you get a positive number. And here, one is negative, one is positive. One is negative, one is positive, so you get a negative number. When we sum those, you either get something negative or positive, depending on if many people are in these quadrants or in these quadrants. So that's why we got a negative correlation here, because we saw actually that most people here, most subjects here, I'll remove all this text for a bit. So most subjects here were in the quadrants where we would get a negative effect for the deviance of your sum, then you get something negative. It's a negative correlation leading to a negative covariance leading to a negative correlation. Okay, that's all I wanted to talk about in this video. It's a lot. I'll put some practice items on Canvas as well, so you can practice this, of course. It is important that you can do this by hand, so you get an idea of how these calculations work. So just take some time to practice it and to calculate these correlations, standard deviations, mean, etc. That's it for this video.